Sorry.
So thank you, Alcin, for the introduction. I hope that I'm speaking loud enough that everybody can hear me.
Yes.
You can see my slides. Yeah, first of all, before I begin, I would like to thank the organizers for this invitation to come to give a talk in this Wombat workshop. I mean, I almost came also to the last edition, but it didn't happen in the end. And I also would like to congratulate them for the courage of organizing this, because I'm involved in this online one-world optimization seminar, and I know how much work it is to have just one talk a week. And now you have for a whole week lots of talks, and yeah, I just congratulate you. So I will talk about a work I did with Felipe Lara from Chile. And we extended the proximal point algorithm beyond convexity to some extent. First, about the motivation behind our work. Yeah, everybody knows more or less that the proximity operator or proximal point mapping, it is single valued in the case of proper convex LSE functions. And in case the convexity is not there anymore, it becomes a set-valued mapping. And one of the ideas we started pursuing was, what about looking for some non-convex functions for which this property of the proximity operator still works, so it still stays single-valued. The second motivation came from the world of mixed variational inequalities. Here, I put here just the mixed variational inequality, just in case you don't remember it at the moment. Basically, when the involved function is proper convex LSE and the operator is monotone or pseudo-monotone, or even some weaker notion of monotonicity, then in the convex case, for instance, when this set is compact, is surely solvable. And there are different algorithms for this. In the last 5 years, we found 3 or 4. For instance, Jura Malitsky's golden ratio algorithm. On the other hand, if the convexity fails or is missed here, then even in the case of a compact set, there may be no solution to such a mixed variation inequality. Existence results in the non-convex case were given by my co-author Felipe Lara and Alfredo Jussem in the recent paper with H taken quasi-convex. So the thought behind the following slides was, let's try to mix somehow their ideas, or to take something from the quasi-convex world in order to make an algorithm, or to design an algorithm, or to modify some algorithm which could solve such problems in the non-convex case. The problem in the non-convex case with such mixed variation inequalities is that there appears some sort of a conflict between the operator and the function. So as I said, even if H is not convex, one can find examples even if K is compact, where such a mixed variation inequality has no solution. Because roughly speaking, T goes upwards and H goes downwards, so if it's not convex and if this is still monotone. What we did was introducing a new class of generalized convex functions. We call them prox-convex. And we have shown that both the proximal point algorithm and this golden ratio algorithm of Jura still converge in the case of this generalized notion of convexity. Before that, some preliminaries. Of course, as I said, one of the problems was, when is the proximity operator single valued? But behind that is also the problem when does it have non-empty values, and we found out that the so-called two weakly coercive functions, proper and LSC, guarantee that their proximity operator is non-empty. Here below you can see some unknown, at least to some extent, property or characterization of an element belonging to the prox of a function, which we used for our technical results. So on the next slide, I will present or introduce the prox-convex functions, how we define them. We take a proper function h, a closed set in Rn, this time such that this set intersects the domain of the function. Of course, later we did k to be also convex, but for the moment not necessarily. And we say that h is prox-convex when its proximity operator of h added with the indicator function of k is non-empty all over k, and this inequality from here is fulfilled for all elements belonging to the proximity, to the image of the proximity operator. If we compare this inequality with the one we have, you see here that this is, let's say, more flexible. In the definition, we still assume that the prox operator is set valued, of course. I mean, for non-convex, as far as you know, they are set valued. But these two things together imply that the proximity operator becomes single valued and moreover formally non-expansive, which are two very good properties for proximal point operators. Yeah, we define by phi of k the set of all such functions on k, and yeah, this k set of course can be taken also as the whole set, but we notice that it works also locally, so on a set, and that's why we defined it by means of a set. One can ask the obvious question, what about the convex case? In the convex case, nothing is broken. This alpha, this coefficient alpha becomes 1, and any proper convex LSE function is a prox-convex on any convex closed set K by taking alpha equal to 1. We have also a counterexample which shows that not all prox-convex functions with alpha equal 1 are actually convex. So this is not an equivalence, it goes just one way. Then we thought, okay, let's look for some functions which fulfill this definition. I mean, this definition is still quite technical, and we don't have a nice geometric interpretation for it yet, hopefully. And we introduced this so-called strongly G-subdifferentiable function on a set. Such a function is defined, you can see here again a quite technical definition, by means of the Gutierrez subdifferential of a set. As you may or may not know, for quasi-convex functions, the usual convex subdifferential is not of much use usually, and that's why there are different other notions of subdifferentials for such sets, like the Gutierrez one, the Plastria one. Aris and Nicolas Hadjisavas have also, Arizanilidis and Nicolas Hadjisavas have also some definition. We took, or we used here in our work, the Gutierrez subdifferential defined like this. Here, this SH of X is the level set at this point. And yeah, we use also the strongly quasi-convex functions, which are defined here. So basically an extension to quasi-convex of the strong convexity. Anyway, this class of functions fulfill the definition of prox-convexity, so at least these functions are prox-convex. And this is, as also the name says from the definition, subclass of the quasi-convex or the strongly quasi-convex functions. So we found the class of functions which also intersects the one for which the existence result due to Felipe and Alfredo holds. But of course, it's always nice to have some concrete examples. And for instance, in this constellation, we have this function, which is of course non-convex, minus x squared minus x on the set 0, 1. This function, as I said, is not convex, but it is strongly G-sub differentiable. It can be shown by just verifying the definition. Its proximity operator is very nice. It's always 1 on all over this set, and as a consequence, this function is prox-convex on the set K. Because it's prox-convex with every possible coefficient alpha greater than 0, it's prox-convex also with a coefficient alpha 1. So as I said before, we have one example where the function is prox-convex with alpha equal 1, but is not convex. This is the one. And this function is also weakly convex in the sense, there are different definitions for weakly convex functions in the literature, but in the sense considered in the proximity world, if you want. But there are also examples which are not weakly convex in this set, but still prox-convex. For instance, such a function, or actually a family of functions, because of course we have here the function, also the set defined by means of an n, which is a natural number. Such a function, I mean, again, 1 minus x to the power of 3 at some points, and minus some constant everywhere else, is by no means convex, is not even weakly convex, is not even lower semi-continuous, but it is quasi-convex. And it is also prox-convex because it, again, fulfills the definition. So again, let's say we found some sort of a place for this new class of generalized convex functions, which intersects the quasi-convex ones, the convex, okay, it contains the convex proper LSC ones, but it also intersects the weakly convex functions, but it doesn't, let's say, completely contain any of these sets. So it's like an intersection of this, and of course, it may be more. We are still at the beginning of our investigations for such functions. On the next slide, we have another example. We tried to find different types of examples in order to understand and to, let's say, feel this class of functions better. X to the power of 3, of course, this is quasi-convex, is even continuous, so more than LSC. But of course, it's not convex. And for instance, if we take the set to be like this, then it's not strongly quasi-convex. So again, if you remember the previous slides, we had that some functions which are strongly quasi-convex are prox-convex. For instance, this one is not strongly quasi-convex. So again, we found, let's say, we draw a line between two classes of functions, the new one and some new one, some known one, and such a function again is prox-convex in the sense we defined. Of course, one can ask, maybe there are other classes which are more or less usable to or useful for different things. What about them? We don't know. At the moment, we worked from this side, from the quasi-convexity, but it is possible that also other types of generalized convex functions are, let's say, good or are parts of the prox-convex world. Okay, not a world, but a class, if you want. So I said that we introduced this in order to extend the proximal point algorithms for beyond convexity. On the next slide, it's just the result, the classical proximal point algorithm formulated, and we take here the function to be LSC and prox convex. The prox convexity involves properness, that's why I didn't put here also proper. We have shown by mimicking the proof from the convex case and changing where necessary, that for LSC prox convex functions, the classical proximal point algorithm still converges towards a minimum of h. In the non-convex world, usually the algorithms converge towards critical points or different such things. In our case, it converges towards a minimum of h, so another useful property. Of course, one can also consider here a set to restrict the function, and still it would converge. We just put it here in the most in the whole set on the whole space Rn, because it's the familiar proximal point algorithm. On the next slide, you see the second motivation, Jura-Malitsky's golden ratio algorithm, extended for such a prox-convex function. So we take, here is the mixed variation inequality. Again, we take T to be the operator to be a Lipschitz, and to satisfy such a monotonicity hypothesis. It can also be taken monotone or pseudo-monotone, but this is an even weaker such hypothesis, or monotonicity hypothesis, also used by Jura in his work, so it's nothing, and actually introduced by Solodov and Zweiter, I think 15 to 18 years ago. And the function h is taken to be LSC and prox convex. The algorithm, the golden ratio algorithm, still works and stays convergent towards a solution of this mixed variation inequality if the alpha, this coefficient which makes h prox convex, is larger than this fraction 2L over phi. And this is, let's say, a way to control the conflict, if you want, between T and H. Again, if H is not convex, it is likely to go downwards at some point, and T is monotone, it goes upwards. So we have a sort of conflict between these two elements of the mixed variation inequality. Yeah, it can be maybe compared to the conflict between the objectives in the case of a multi-objective or vector optimization problem. Yeah, also there we don't have a point which satisfies or is minimal for every function. Usually, then you have to find some sort of a compromise, like the Pareto efficient solutions. In this case, a similar thing happens, but it can be, so we can still get a solution to this this mixed variation inequality if it exists, but this existence is a hypothesis in all, even in the convex case, for such algorithms. If this happens, in the convexity case, if alpha is equal to 1, this condition becomes this one, which is basically the condition used by Jura in his work in order to get this convergence. So in this sense, at least, we have an organic extension of his algorithm to this prox-convex setting. Of course, one can ask, yeah, it's nice, but this is only the most basic algorithm in this case. What happens in the case of step sizes? Because if we took here just step sizes to be 1, if we introduce also some step sizes like lambda, so prox of lambda h and so on, then the hypothesis has to be modified in a sense that both h and alpha, lambda, h, where lambda is again the step size, have to be prox-convex. If we assume these two functions to be prox-convex, then we can add here a lambda, so step sizes, and the algorithm remains convergent under the same hypothesis. And I think lambda should play also here a role. Is lambda alpha greater than or equal to this guy? We also implemented our algorithm for some examples. You can see here a mixed variation inequality. Again, it's a non-convex one. We have this conflict. T of x is a very nice operator. It goes upwards. H is a non-convex function, but it is prox-convex, and it goes downwards. So we have a conflict. The question is, where can you find a solution, or how can you find a solution such that this whole sum stays non-negative? One can calculate it even by hand. It's x bar equal to 1. And we have here some implementation, computational results for different starting points. And as you can see, the algorithm, so the golden ratio, Jura's algorithm again, works nicely and delivers the solution after a reasonable time or number of iterations for different errors. So it works, so the theory is also illustrated or is proven right by this experiment. We also took a more complicated function, function and operator, so a more complicated mixed variation inequality. The one from here, again, here you have a non-convex function involved, h, which is prox-convex, and an operator which is quite nice, but again you have the conflict because in the first variable the operator goes upwards and the function goes downwards. And for alpha taken like this, we got again we obtained again the solution after a very reasonable number of iterations. In each time, for each I took 4 different errors, and in each case we got the solution quite quickly. And of course, as I said, we are at the beginning of the work on this class of functions. Then the next step, I mean, I listed here some future ideas, some things we are currently working on, some calculus rules for such functions, because we noticed that they're not, the class is not even close to multiplication. So as I said, for the golden ratio algorithm, for if it works for h, adding a step size, one would have to add that lambda alpha h is also prox-convex. So it's not sure under which hypothesis a prox-convex function multiplied by a constant stays prox-convex. Of course, for some example it works, but for some other examples this doesn't work. So we are still to find out what exactly controls this thing. Then we are also working on extension to splitting methods, forward, backward, or Douglas-Rushford, Hilbert spaces, because what you have seen is in Rn. And other ideas are to extend other algorithms, not only Jura's golden ratio, but there are also other algorithms for solving mixed variation inequalities, and some recent ones. And we also are currently working on extending also some of these algorithms for prox-convex functions. So this was my talk. I thank you very much for your attention, and I think we may have time for questions, I hope.
Thank you, Sorin. Any questions or comments for Sorin?
Yeah, I have a question. So thanks. Can you hear me okay?
Yes, please go ahead.
Okay, yeah, okay. Thanks for your nice talk, Sorin. So I think probably the answer is it's difficult, but could you imagine defining a kind of like it's no longer prox-convex, but like resolvent monotone or something like that? So doing this with monotone operators instead of convex functions somehow?
it's possible. We didn't thought about this yet because we are still trying to understand the functions or the structure of this class. As you have seen, it intersects different classes, but it's not. We cannot draw it, for instance, nicely and so on. But it can be. I mean, for maximal monotone operators, you know, the resolvent is nice, and if we go beyond that, the resolvent is not nice. It can be. I mean, we can find the class, or I don't know, extensions to the Banach spaces. Again, the resolvent is not very nice there.
Sure.
It can happen. So it could be an idea. Yes.
Yeah, I guess the main difficulty is probably that the definition uses function values. So maybe this could be a problem. But yeah, okay, thank you.
Yeah, thanks.
Okay, Sorin, there is a question in the chat box. Could you see, please?
I'm trying to
from
find the chat.
Constantin Zalinescu. If you can't,
it's a misprint. Yeah, it may be. The inequality must be strict, otherwise the function. Yeah, thanks for the observation. Probably we have a misprint. I agree with you. I mean,
any other comments or questions?
Definition
okay, you want to check that first?
Yeah, I think you're right. Yeah, I will correct for future talks, and I have to check also in the paper. Maybe we put it. But okay, thank you very much for the comment.